It should have created a new project. And a project is just a folder where you keep measurements in and essentially we keep these tasks. So
Okay.
you want to create a task in that project.
Okay, so create, okay.
Yep.
Okay.
And now it brings up a menu with creating a task.
Yeah.
And it should look a little bit like this down to
Yeah.
the right.
Looks like this
Yes.
here.
So what you want to do is you want to select the spread and protocol that's relevant for you. So you want to select a 4x12 spread. So if you use the mouse buttons to move the yellow window up on spread.
Okay, yeah. 412, yeah.
Yes, exactly. So once you're there, you can use the side mouse buttons to switch between the different ones. But you want yours to be 412.
Okay.
Yep. So if it's 412, then you can go one down with the arrow to the protocol.
Okay.
And there you can now see the different protocols that are available for the 412.
Okay, so we have Warner, we have dipole, gradient, XL, Schnur-Purgé. Okay.
Exactly. And that's how you select the different array types is by
So in
choosing
our
the
case, we
protocol.
will select like gradient, for example.
Yes, exactly.
And this has nothing to do like, so the protocol, like, because this protocol, sometimes they have, the spacing could be like not uniform between electrodes. So the
So the protocol essentially what it does, all of these things assume uniform spacing of
okay,
some setup. And then what it just does is essentially the spread tells it, okay, I have 12 outtake, I have 24 plus 24, I have 48 electrodes, and I want to send power to all of them. And then the
okay, I see.
protocol tells them in which order to send power and measure potentials.
Okay, that's
So
great. So I don't need to like change spacing or anything. It's
no,
just like
no,
it does this
exactly. It does
automatically
all
for
of
me.
that.
Oh,
Uh,
that's
and
great.
and there's text. You can personalize protocols and load them onto the instrument. There's text on the website to explain that. But generally, the ones with the instrument they work fine for a huge array.
Yeah.
The one thing you need to do here is to choose the minimum electrode spacing. So I don't know what it's saying right now on your screen,
Right
but
now it
for you,
says one, so that's basically
oh yeah.
yeah.
So that's 1 meter,
Yeah,
and
1 meter.
that's what you want to do.
Yeah.
So great. If let's say you want to use it at the 2 meters extent, then you go onto that option and you press OK, and then you get into an interface where you can like choose numbers,
Okay. Yeah.
and then you would choose it to 2 if you would do a 2 meter spread.
Okay. And
So,
then
but
minimum electrode spacing in the y direction, we are not doing this. Yeah. And
yes,
minimum electrode.
so other spreads are like if you want to do a 3D setup where you have multiple next to each other, and then you might have a Y spacing, or if you go down a borehole, you have a Z spacing. But the standard spreads just on the surface are just in one direction.
Yeah.
So
So what we are doing, we don't need to worry about the other.
exactly.
Yeah.
So once you have the spread you want, 4x12, the protocol, gradient XL, and the minimum electrode spacing 1, you can press OK.
Mhm.
And it should create a task now.
Yeah.
Great. And then it has automatically jumped into the settings. So that's this window that you're seeing, right?
Yeah. Mm-hmm.
Cool. So what you can also, if you press the menu option again, this one,
Yeah.
you can see you can see where you would find the settings otherwise. So in the settings. But yeah. So that's where you would that's where they are, and that's also how you would get back to the task. But you're in the settings, so let's talk about the settings. So if you can go to the receiver settings, I think that's where you were. So if you just press OK,
Mhm.
the receiver settings has a bunch of different things to look at. The measuring mode, and actually, can you try to press the active guidance button? That's the speech bubble
Okay.
on the top.
That's yeah. Mhm.
It should actually now load you a text that gives you some information about the different options here.
Yeah.
So you can always do that. It's the same, or you can read it in the manual or in the quick guide that I just told you.
Yeah.
So it has the resistivity and res IP.
And we
I
generally
believe
do the res IB because you said like this induced polarization will.
yes. So there are different things. The induced polarization always exists, but
Okay.
if you measure just if you don't want to use it for anything, you can just measure resistivity because you measure at the end part where it doesn't affect the data. If you want to use it, then you want to use the res IP measurement. Um, the thing with res IP measurement is that the standard model does it at 50% duty cycle, so it takes longer to acquire. It doesn't do the 100% duty cycle measurement. So you will be using, as long as you don't want to look at IP, you'll just be using the res as the setting.
Okay, but if we so you can get resistivity and you can then induce polarization also measurements.
Yes. So if you
Usually
do,
the induced polarizations that would be helpful in differentiating like salt water from fresh water in sands, for example.
yes, so like salt water from clay is the classic
Yeah,
example,
yeah,
is because clay has an IP
yeah, exactly.
signal,
Yeah, sorry, yeah.
whereas
Salt water
salt
from
water
clay. Yeah,
doesn't.
yeah,
Yeah,
yeah.
exactly.
Salt water
So
from clay.
that would be the classic examples where IP would be useful. So,
Yeah.
um, I yeah. So that would be the way. So yeah, but this is a world where you have to know if you're going to use it or not.
Yeah,
If you're not going
and
to,
like for that field trip, what we'll be doing next week, we're not gonna use it because that's an agriculture site, so we don't need it.
no, exactly. So if you want to use it, you can use res IP, and then you acquire it as well. So, but yeah, but this is how that's how you do it. You choose res IP, and then you can select the IP as well on it. If you're not going to use it, you just use resistivity. But yeah, but exactly. But IP is because some materials have the same resistivity but don't have the same chargeability. So in some situations, it can help to also look at
Yeah.
IP. That's the top measurement mode. Then you have the number of stacks. So the number of stacks and the error limit is essentially how often it repeats that waveform to get below the error limit. And the error limit is essentially the noise from each part of the waveform. So remember we had that these square stacks. If they vary too much, that is an error between one measurement and the next. A very standard one is to have it between 1 and 3. Essentially, that means that it'll do one measurement, and if the variation is too high, it'll repeat up to 3 times to get the error limit below, to get the error below the error limit. So if you're in a high noise environment, you might want to increase the error limit to 2% and then increase the number of stacks. So, but in most environments, these types of settings, so 1, so 1 and 3 and 1% should be good.
Oh, so here it say like minimum number of stacks, 1, maximum number of stacks. So we set this to 3.
Yes, exactly.
Okay.
So in almost all measurements, it'll just measure 1 because it'll be fine within the noise level. But in those cases where it doesn't, then it can measure an additional time.
Okay.
The number of current pulses is only relevant for a res IP 100 setting.
Okay.
And I believe that your instrument doesn't do that. That's why it says only advanced instruments. Delay in acquisition time is also relevant with IP. So if the classic one is this 0.4 and 0.6, so that means you have a 1 second waveform and you measure the resistivity value in the last 0.4 seconds. So the first 0.6 seconds you don't measure because you think that's where the IP is happening. And the last 0.4 seconds is where you measure the resistivity. So the full waveform, I think you have the basic version, so it doesn't. Does the full waveform show up on the screen there? On your screen?
No.
No, and that's because in the
number of window record full waveform, record full waveform, yes. Choose.
Yeah, can you choose it? Can you choose it? Can you choose yes or no?
No. I
No,
think
and that's because that's part of that's not part of the basic feature then. I just need to remember it's part. Essentially, what that would do is it gives you for every sample rate, it gives you one value, and that allows you to analyze the waveform afterwards for noise quality and stuff. But in the basic one, you just get the resistivity value out.
Yeah.
The sample rate, it gives how often it measures to create the window. Generally, a higher one is better, but it also fills up more data if you do the full waveform. So for your case, you just want to use the high one.
Yeah, so here it has 1,000 and 1,200.
Yes, and that is perfectly fine. Then there's power line frequency. So you want to have yours to say 60 hertz because you're in the United States.
And this is just to filter out power lines.
So that's why the sample rate says 1,000 or 1,200. Is that 1,200 is for the 60 hertz and 1,000 is for the 50 hertz setting.
Okay.
Yeah, and that's just for the power line noise. So essentially what it does is it measures at a multiple of 60 hertz and thereby essentially phases out the contribution.
Okay.
So that's all of the receiver settings. This essentially says where do I want to find my resistivity data and what's the shape of the waveform where I want to find it. Let's go to the transmitter settings. That's the next one over.
I click OK or I just...
You just press the square one. Exactly. There we go to the transmitter settings. Okay. So, and we went through some of these initially. The minimum and maximum values. The minimum value doesn't force it to use that current. It just says the minimum value you're happy with. So you probably want yours at 0.5.
Minimum is 0.01.
0.01. That's probably okay for your use as well.
No, 0.1, not 0.01, 0.1.
0.1. 0.1 is probably fine for your application as well. Okay. So 0.1 maximum current is what it tries to. That's the maximum it's allowed to use. It will actually choose the one it can to get the highest voltage, but you can just set that to its highest value. The higher values will use more energy during a day. So yeah. And that's all of these settings. Essentially, we just want to have these as high as possible as the energy allows. The electrode test, you want that on as yes for the first setting of the day. So for the first time you measure for a given configuration, you want that to be yes, because what it does is it tests every electrode and then gives you a result of how good the contact resistance is. Okay. So it's like a quick in the field QA test, because it also tells you if you essentially also you can see then if you do it and every electrode is not connected in the cable, that means you haven't connected the cable. So it's a great QA test in the field to do to figure out the elements. The bad and fail electrode are essentially values that gives you information about the electrode test when you look at it. The electrode test current, you don't really need to change that. The only place you might want to change that is if you're doing IP. If you're doing an IP survey, you generally want to have it lower because it just gives an initial small polarization of the electrodes. But as again, the quick start, it just tells you, do not change. So just keep it as it is. The load variation margin, you want this to 10%. You can press guidance on the instrument to learn more about it, but essentially that sets how much the instrument is allowed to change its load in a single measurement. But in order to be able to change it that much, of course, you need to reserve it. So you have it set too high, you'll always transmit at a lower voltage. So keep it at 10%. That's a good value.
Okay.
Cool. And those are essentially the settings. The next window, the next one is IP settings. There's more text to it in the thing. You won't be using it, so it doesn't really matter. But yeah. But that's essentially, having done that, you could start a measurement. So the way to do that is to either press the play button, or you go to the menu and choose measure.
Okay, so go to the menu here, right?
Yeah. And choose measure. And there you can press OK and start measuring. Of course, now you're not connected to anything. So
so station position, electrode distance. No, like when I said measure, I got this menu.
yes. So it creates this window, right?
Yeah. Mm-hmm.
Yes. So let's say that you have all 4 cables out.
Okay.
You have the instrument in the middle. What you then do is a 4 cable no move type of station.
Okay, so you type of station position, electrode distance. So I put the electrode distance 1 meter.
No. That's the position along the electrode line, and the instrument always begins at 0. So
okay.
Yeah. But what you will do is have a 4 cable no move with the instrument in the middle of the 4 electrodes.
Okay.
And then you press OK, and it will create the measurement essentially. Let's say you had just done a roll along, you had moved 1 cable ahead, then you would choose the 1 cable forward type of station.
And then like 1 cable forward, basically like you just remove this 12 electrodes, put them over there, and then
Yes.
you have to unplug all these connectors. And
yes, you unplug every connector, you unplug
yeah.
all of the electrodes, you roll up the cable, you walk to the other end, you roll it out, you put all of the electrodes down, you plug them all in, you move the instrument 1 over, and
Okay.
then you do and that's a 1 cable forward.
Okay. So basically like you leave like, so like in our case, like we have like, let's say 48 of them. So basically like you leave 36 of this electrodes in the ground as they are. You only move 12 to the other side, and then you unplug everything and move the instrument and everything.
Exactly. So what you would do specifically is you would take everything from cable 1 here
Okay.
and move on the other side. You would move the interconnector to there where the instrument used to be.
Yeah.
You move the instrument to there where the next interconnector was, and move that interconnector between the cable you just moved and the previous one.
Okay.
So you
So it
essentially
only saves you the effort of just putting this rods in the ground. Yeah.
Yeah, well, I mean, yeah, exactly. Well, it saves you the
For
effort
3 of them. Yeah.
for 3 cables,
Yeah.
and it puts all of the data into one. It moves
Okay.
all of that measurement for the long line into one project file that needs one processing. So what it really does is it makes it way easier to handle the data afterwards.
Okay.
And it does it all in the same setting, so it does it natively. So yeah, so when you do that, then you can start measuring, and it does the electrode test, and then it tells you every electrode is disconnected. But yeah, if you have the safety switch in, you have this warning of safety switch stop. So if that's the case, you need to take out the safety switch. That's a big red button. And that's essentially the secret behind starting a measurement with the terameter.
Also, when you do this, you need to set on the switch. Is that what you said?
So if the switch is not depressed,
Okay.
it will just measure. So, but if it is depressed, it will give you this warning, safety switch stop. So it will refuse to measure essentially. And
Okay.
that means you need to take out the safety switch.
Okay.
Yeah. And you can try it right now. Try pressing it in.
Try the safety switch.
Yeah.
Okay.
And now
Yeah.
the instrument should say that the safety switch is on.
Yeah.
Exactly. And if you take it out,
how
you have to like twist it. Yeah.
Okay. Start measuring.
Exactly.
Yeah. Okay.
So that's how you use the safety switch.
Okay.
Okay. So when you are setting up these electrodes and these stuffs, you need to press that
Yes.
one, right?
So the good practice is to have the safety switch in while you're moving electrodes, connecting electrodes and everything, and take it off when you're about to measure.
Okay.
That's a good practice. And what the safety switch does is it physically disconnects the instrument's power supply from the electrodes. So there's no way to accidentally send anything. If there's anything wrong, or like in normal use, the instrument should never accidentally send a current. But if something breaks, it might. So the safety switch is just a way to ensure that there's no way to accidentally send a current while someone is using it. Yes. So that's how you would start a measurement. The electrode contact test. Actually, you can start a measurement right now and see what it says.
So so now let's start the measurement. I just click OK.
You can click OK or click the play arrow.
Okay, play arrow. Okay, say warning.
Yeah, so it gives you a warning essentially saying, make sure no one is touching any electrodes.
Okay.
And don't use in a thunderstorm.
Okay, so now I clicked OK.
Yes, and at the bottom it should say testing electrode.
Yeah.
Yeah. So what it's now doing is it's trying every contact, and it's just using that small post to test the electrode. And I think there should be 48 electrodes or 47.
Yeah, yes.
Yeah, 48. Good. Cool. And now we can see the electrode test results. So if you move to this window, I think it's actually the other way. So I think you can either go all the way around or it should look like this.
This one.
I think it might be another. I think it might be two more.
This one.
Yes, exactly that one.
Oh.
I can just press once.
Oh, here we go.
Yeah. So that should show the electrode result, and I think it should say fail on all of them.
It's saying not contact. No contact.
Exactly.
Yeah.
No contact. So it is what is essentially said is, okay, I tried the contact of every single electrode, and every one of them has no contact.
Wait.
This is good because there's no electrode connected.
Yeah.
This window shows what it might look like if you had them connected to the ground.
Wait.
So you have to take out. So this top one, this is the cable 1.
Okay.
And cable 1 is always relative to the instrument. So it's always the cable that's 2 away.
Okay.
So that's what's meant with cable 1. And then it has the electrodes, and then it has the electrodes 1 through 12. That should also be what you can see. And then it should say cable 2, and then 1, and then 2, 1, 2, 2, 2, 3.
Yeah, it does this, yeah. Mm-hmm.
Exactly. And it does that all the way down to cable 4. So
yeah.
The position of every electrode should also be they should be incrementing with 1 meter.
Because we are setting it at 1 meter. If we use the default value, it would be incrementing at 2 meters. So it would be like 2, 4, 6. Okay.
Yes, exactly. So that's what it's using to do things. Yeah. So in this image, it's using a ½ meter spacing.
Yeah, maybe the first time we use it, we just do the 2 meter.
Might be easier, but yeah, just to get acquainted with it.
Yeah.
Yeah. So the ohm meters, that's the contact resistance, or the ohm. So that's this value here. And you want this value. So of course, in yours, you have no contact.
Yeah.
So you have no contact resistance. But let's say you were in the field.
Okay.
You want this value to be consistent in the area.
Okay.
So the absolute value will extremely depend on the ground conditions.
Okay.
But you want it to be consistent. So sometimes, let's say this one, like all of these 130, and this one says 2000. that means that electrode has bad contact.
So you put salt water, or you put water, or
exactly.
You put clay,
you might go and check, is it connected?
Okay.
Then you might see like is it, because if it's like in the ground and it's loose, like there's like the ground is shifted around it and it's loose, you might just like put it in another place right next to it, like what's actually contacted. Or you might add salt water, or you might add a second electrode right next to it, like just anything to increase the contact.
Okay.
And then when you press run again, the electrode test will only test the electrodes that failed by the failed criteria. So essentially, you can use that to make sure. Sometimes an electrode, you just can't get the contact. Maybe there's a rock right where you're putting it in. And what you can then do is you can press Option on the key. If you select on yours, you can press Opt,
Next
OPT. That's this in the bottom.
Oh, okay. Yeah.
Yeah. And it should, and there you can have the option to deactivate an electrode. So you can choose to exclude all bad electrodes. You can choose to exclude this electrode. So.
Oh, okay.
Yeah. So that's where, like, let's say there's one electrode that you can't get a contact to because there's a rock right below it. Then you just exclude that one. And what this does then is it removes all of the measurements that would have used that electrode from the protocol. So instead of getting bad measurements, it just removes it, so you don't get bad measurements using it.
Yeah, here say like use all bad, exclude all fail, exclude all bad, enable all, clear all. Okay.
Yeah. So those are the options you can use to go through it for measuring. When you measure, you can use the other windows to look at incoming results and so on. You have to see this in the field. There's really no way to show it working without measuring. So,
yeah.
But every single one of these windows has some information to look at. So, there's also the pseudo section, which will show you a pseudo section in the field. I actually think the manual has more images on that. Let me see.
So the pseudo section, what do you mean by the pseudo section?
So the pseudo section, that's a good question. We saw pseudo section before. Let me find them in the manual here. Control F. Pseudo.
So this is the one before inversion?
Yes. So the pseudo section is essentially the same as the VES profile, but in 2D.
Okay.
So it's the apparent resistivity for all of the points you've measured so far. So it gives you this image that's not an inverted section. It's just the apparent resistivity.
Okay.
And it can give you an idea of the general trend of things, but it can't be interpreted really. But it also gives you an idea of where you have data now and where you do not. So this is how the pseudo section will look like, and it updates after every measurement. So.
Okay, but you said it cannot be interpreted. Like you
yeah,
can,
like it can be used very
high
loose
resistivity value and low resistivity value.
So it can be used very loosely to say, okay, there's something more resistive deeper down and something more conductive near the surface, but you can't use it to get the absolute values, and you can't use it to get like the borders. So it can be used for a loose overview, like, oh, okay, we are seeing the surface clay layer that we expect, and we're seeing something more resistive at the bottom, but it can't be, so it can be used for quality assessment. It can't be used for like geological interpretation.
Okay. So it can be used basically to guide your work here.
Yes, and to get an idea of like, are we getting good data, and are we getting value? Are we spreading the area as well? So that you can see this during measuring as well. And the other one is this option, which allows you to see the standard deviation, the voltages you're using, and the apparent resistivity directly. That will show up for all of the ones that you're currently measuring on. It also, this one, the TX, it will show you which TX electrodes are being used and what the input current is.
Okay.
So these will all appear during measuring, essentially. Is all of these windows. And this is all in the user manual, and there's a lot of text in the user manual to explain details.
And is it a common practice that, like, for example, like I have this electrode setting, before I change it, can I just change the, like, from Werner to Schlumberger and make another measurement?
So Yes, there are two ways to do that. Way number one is before you move the instrument is you create a new task.
Okay.
And then in that task you select a Venner setup, and then just measure the Venner. The other one is that you can actually make a custom protocol where you add the Venner ones in and then measure it all at once. So, but usually people want to look at them separate.
Okay.
So what you do is you create a new task,
Okay.
and then when you move the instrument, you make sure to select the task, the other task again.
Okay, so you do it with this task, then you select the other task, you do it with the other task, and then you move the instrument.
And then you in one project you'll have two tasks essentially.
In one project you have two tasks, and that will generally be better because you will can.
So
you'll know
I don't
more
know
about
if it's
the
generally better,
uncertainty.
but that's generally what people want is to have them separate. So yeah.
No,
I
I
mean,
mean it's better to have like more than one setting, like Werner,
yes.
Lompoget.
I mean, and that's why and if you always do it, so it's like if you're always doing it both a gradient and a dipole, it would be worth looking into creating a protocol that includes both of them in the same measurement.
Okay.
So if you're always doing it, if you're just occasionally doing it, it might not make sense. So yes, but that's the gradient. So this is essentially the task. And if you have, so you might have gradient one and dipole one, and then you measure the one, measure the other, and then move along.
And generally, like for you, when you go to the field, do you generally measure several of them, or you just go with one, like the best ones that you see?
So I almost always will not measure several. I'll measure the best one, which is in most of the situations where I've been in, it's been gradient XL.
Okay.
That's the one that's best in the Danish geology. And sometimes we've created custom ones, which are like gradient XL plus additional dipole measurements.
Okay. So
yeah.
basically, for me, I think I will just be using gradient also. Yeah.
Yes, gradient. You should try it doing gradient and dipole first and see which resolves what you're looking at best.
Okay.
So because dipole and gradient have these slight differences of which types of structures they resolve. So but that's a thing that comes from experience and the geology you're looking at. So in the geology in Denmark, there's almost nothing vertical. So that's why dipole is not that useful because there's almost nothing vertical to look at. So and that's what dipole is really good. So, but yeah.
In our case, we have sand clay on the top and then limestone at the bottom. So.
Yeah. So I mean, and gradient does a good general job. It's like a good generalist of one. So and dipole can give extra information if that's what it gives. So yeah. So Venner and Schlumberger are essentially subsets of gradient if you think about it. Venner is a gradient array with a fixed geometry, and Schlumberger is one where you vary the outer electrodes. But essentially, so they are subsets. They're all nested arrays, is what they're called, nested arrays. So gradient, Venner, and Schlumberger are all nested arrays. So yeah. Yes, that's essentially the things for measurement. We can have let's have a look in the last 20 minutes here. Let's have a look at the software that you're using to get the data out of the instrument, and then in the instrument. So in the instrument, you can have USB stick connected, and then you can export data. That's also explained in the manual. You can use this export function if you have a USB stick in or an Ethernet cable. But let's say you.
So these, you mean these one?
Yes, exactly. So either the SD card or the USB cable, you can have them in the instrument, and then you export a project to that instrument.
So I put this in the instrument.
Yes, there's on the side it has the SD option. There should be an SD card inside of it that you can add to the instrument.
Does the instrument has also its own internal storage, or?
It has an internal It has an internal storage that's quite big. So during measuring, it will always add to the internal storage, and the internal storage is big enough that you can have many measurements on it. But it's good practice to take the data out after you're measuring, just in case.
Mm-hmm. How big is the storage? Like in
I don't know what's on the newest generation. I think it's like over, I think 256 gigabytes. It might be more. But it's the normal projects don't take up that much room. But yeah. And it will give you a warning if it ever reaches its maximum output. So I think inside of it there's like a micro SD, but if you try the Ethernet slot, that one is easier to see.
Oh, the Ethernet slot.
You can use
or the USB slot. You can also
slot.
you can also connect with a Ethernet cable and use like its IP to connect. But if you have the USB, you can put it in there, and then you can export a project to it. The export procedure is explained in detail in the manual. So, but let's say you've done that.
Okay. So
when you then,
well, I mean, what's the difference between? I mean, these two are the same. Yeah? These two are the same, right?
Yes. So that one is for that one is a micro SD card reader for your computer. So if you use a micro SD card, you can use that to read it on the computer. So that end would go into the computer.
Oh, this goes to my computer?
Yeah, you will.
Yeah, so that goes into your computer. That's a reader. That's the micro SD reader.
Yeah.
If you're using it. Yeah.
I got it.
Oh, and then it connects to the
yeah. So you would put a micro SD card into the instrument and export to there, and then take the micro SD card out.
Then we'll take this one and put this one. This one is a reader.
Yes, that's a reader. Exactly.
It's not. Yeah.
Yeah. So that's an alternative to the USB stick. Yeah. But it does the same thing. It's just yeah. But let's say you've exported it. What you then do is on your computer, you want to download what's called LS Toolbox. And I'll send you the link to where you can download it. Essentially, here we go. In the resource center of Guideline Geo, and it's called here. Let me choose it. Well, there we go. It's called ABEM Terameter Toolbox.
Okay.
And what this does is it's this software here. Sorry. It's this software that allows you to access and get some information about it. So what you do is that you create a project group, then you can add a project, and let's say you've put on a USB stick, put it onto your computer, like I have here, and I can then I can select the project and open, and then it just gets added here. Like if it was project 7, then it would show up as project 7. And this project 7 has 5 different tasks. So every task will show up here as a different one, and we can see different values on it. Let's say here, I can see the summary. That just gives me the position, some general information. I can see the electrode contact test. So this is the electrode contact test for the final measurement. It just shows you how it is in general. If there was someone that was super spiky, then you can see it here that occurred.
Okay.
So this allows you to, after the fact, look at it as a form of QA. You can see the pseudo section. You can see this is actually an example of where someone flipped a cable. So that's why the data here looks really weird. Let me open another one. Let's look at this one. I think this was a good data set. Yes. So this is how a pseudo section might look like. This is just generally resistive. And then here, these ones are negative resistivity points, so those we want to process out. We can also look at the table view.
And this negative resistivity point, could this be like pipelines, or is this just errors?
So they can come from a couple different sources. If there's like a pipeline that's extremely conductive, it might appear as negative resistivity. If there's if there's like a 2D structure running parallel, it might appear as negative resistivity, or it's just an error, a measurement error.
Okay.
So there's some cases where if you have big lateral changes along a profile, that the parent resistivities become negative. Let's say in your profile, you have highly resistive sand, just dry sand, and then very resistive clay. Measurements that go across that border are doing an apparent resistivity, which assumes the ground is homogeneous, but in reality it isn't. And then the measurement can appear negative. In that world, those are consistent, though. Like there will be a consistent grouping of negative values, whereas here you can see these are just individual random points.
Yeah.
So individual random negative values are almost always just noise that need removed.
Okay.
Yeah. The table view will show you every single measurement with a bunch of these different configurations, and you can use it to do some quality control. So you can sort it by voltage, and here, for example, we can see, oh, they're negative values, and you can actually then in here select them and filter them.
Okay.
So now those have been deactivated before they go into the processing. So this toolbox is a way to just do some initial quality processing. Maybe you can see at the noise, that's a variation percentage. You can see like, okay, there's some, let's say our noise floor is 1.5%. Then we can take all of the values with a noise above that and filter them. So that's just that. So these are just different ways of doing the processing. And if we're happy with our initial processing, we can then choose to export. We press export here, and we'll be using res2d-inf. So what you want to do is you choose all of the arrays you're using, choose res2d-inf, and then you press export. And this creates a res2d-inf file with all of the data.
Okay.
And then you can open it in res2d-inf to invert it. But yeah, but the LS toolbox is just free from the website, and it just allows you to essentially look at the data, have an overview of it, and so on. So this will be step one after you've gotten the data out of the instrument onto your computer.
Okay.
Is to open it in LS toolbox and then do these initial processings. Finally, I'll just briefly show you how it looks like in res2d-inf. So res2d-inf, when you have it open, you can load data. Let's say
so this is the software that will do the inversion, yeah?
This is the process. This is the software you do the inversion in. Exactly. Okay. So here I'll load the data file we just looked at.
Okay.
And this is how it looks like. The Sequent has their own guides on how to do the processing, but essentially here we can look at if things are stable. This series here are like where they're very different from their neighbors. So it might be signal, it might be noise. What we can do is that we can do processing here. We can choose individual focus points. Every one of these, you can see I have this selected. It has these dots. It shows me which electrodes were used to measure that point. Then it just gives a pseudo section, and then I can run an inversion on it. This training doesn't cover any of the settings or so on for the inversion, but one can run an inversion. Let's just assume it has fine settings. I don't know for this one. We can see it's running the inversion now. We can see the misfit. We can see what it's calculating. It says it's done. And then we can look at the data. And this down here is our model, our calculated resistivity model. And I can.
So the first one, like the first two, these are raw measurement.
These are raw measurements. These are the pseudo section. So these are the measured pseudo section, the calculated pseudo section, and then and then the inversion result. And we can see is it has a misfit of 5%. And this is generally too high. So we generally want a misfit below 2.5% if possible. And the reason is,
what do you mean by misfit? Misfit between what?
So that's the misfit between the model and the data. So this model is essentially, it's the difference between this calculated pseudo section and this real one. So it's the difference between the result of the model and the data. So what we probably want to do is that we want to disable these points, because these are probably, or these are what we can't fit. So and because so this might be, and that's a dangerous thing. They might be signaled, it might not be. This comes on experience and so on. If we assume that they are noise, we could deactivate them, save this, save it as edited or processed, and then do the process again with running it. But this is how that works. But essentially what you do is you export the data to the you export the data in LS Toolbox, you load it into rest2the-inf, you can process this in rest2the-inf, and you run the inversion in rest2the-inf, and then you end up with these 2D pseudo sections.
Yeah, so you end up with so this with like the final one that this one.
Exactly. So so in the very end we might let's
okay. So you got like these resistivity values.
Yeah, you get this resistivity value, you get this map here, and then you might want to and then you can use this to interpret on. So in this case, we have this conductive near surface body, and then more resistive underlaying elements. So
yeah,
and I don't, this data is not anything I've looked into in detail, so I don't know what the geology is like there. This is just random data from India.
Yeah, it could be like, it could be just like a big clay unit.
Exactly. It could be a surface near clay unit and with then dry sand beneath, and then maybe wet sand over here where it's more conductive.
Like in our area, that would be the limestone.
Yes. So in your area, the more resistive body underlaying it would probably be the limestone.
So if that was in our area, that would probably be like the red one and the purple ones, that would probably be the limestone.
Exactly. And then the surface ones would be intermitting between clay and sand.
Yeah.
Yeah. Is your limestone saturated? Is there water in it?
Yeah.
So
could be saturated. Yes, most probably it will be saturated, like not on other parts where it will be dry. Yes, it will be saturated.
Yeah. So then it will be high resistive mixed with whatever it's saturated with. So fresh water is usually also resistive, but it should generally it will definitely be more resistive than the clay and sand. So yeah. But that's essentially, that's the theory of ERT. It's the instrument in particular. It's the instrument setup. It's getting data out, and very briefly the software is inside. I think that wraps up our half-day training.
Yeah, that's great. Thank you very much. So with respect to this, like the inversion software, so is it easy to use it, or like there is a manual to see how to use it, or?
So Sequent, which are the people that provide the software, there's manuals to use it, there's training videos to use it as well. As with any inversion software, to using it best requires experience using it. But there are manuals, there's help options going through it. So, but those are all provided by Sequent, the details of how to operate and so on. They also have a wiki that you can use to get more information. But yeah.
But like, what is the learning curve of this? Like, how long you will need to spend?
So if it's clean data, then the learning curve is a couple of hours of looking at it, perhaps. It's when it comes to the details, it becomes difficult. If you have very big topography differences and you want to add it in, if you have high chargeable differences. So yeah, so it's not easy to say one answer. It'll depend on the geology you're in, and it will depend on what you're trying to extract from that information. I mean, in its very basic form, it's removing some outliers, running the inversion, get the misfit as low as possible, and that's fine. But that's only really ever the case if it's like great data with no noise and so on. So yeah.
Okay, if there is a data that has noise and things like this, then you need to put some constraints yourself.
Yes, so what you need to do is like do processing. So in the data here, you might have to remove some, like if they're very noise affected, like these measurements you might have to remove. You can see here the dots missing.
Okay.
These dots that are missing were the negative values that I didn't export from the toolbox.
Okay.
So that's the type of processing that might be needed. So like I might here actually you can select them and disable them as data points. And you can see now it's totally different because it doesn't have those outlier data points. So
okay. But the bottom line, like if you give this to like an undergraduate student, he can figure it out on his own, like.
Yes, using the teaching materials available by Sequent. Yes.
Yeah, you'll be able to figure it out.
So at my university, we essentially taught softwares like this in basic use in like a 2-week, so like 6 hours in total is what we taught bachelor students to use the software at a decent level. So yeah. And that's going through examples and so on. So yeah, Sequent, they also have example data sets that you can work on to run inversions on and so on. But that's all, provided by them.
Okay, because I will probably give this to a student who will figure it out. So he can easily, like through this material, he can easily figure it out.
Yes. So and they have a lot of material. They also have YouTube videos on how to use some of them. So it's definitely, and res2dinf is so universally used. There's lots of materials on it. So yeah, a student with time and a bit of knowledge and research can figure that out. Definitely.
Okay. Yeah. Yeah, they have time. I don't know if they have knowledge in research, but they have time.
I mean, they can get it probably. I learned it as a student, so I assume that other people can as well. Good. Well, were there any other questions?
Not really. Not at the moment because we still didn't use it. Probably when we start using it, we'll have like tens of questions.
Yes. So now, again, I'll refer
one
you
question
to
at the end in terms of safety. I'm sorry.
Yeah.
Do you have some tips about safety maybe in using this? How dangerous is this one? Maybe when you just this electrode is something during workings. Yeah.
Yes. So generally, when operating, when you're not measuring, keep the safety switch on. And if that's on, then nothing can happen. While measuring, keep an eye over the entire section you're measuring. And if you see someone or something, like if a dog is running towards the electrodes, press the safety switch. It will safely interrupt the measurement. And and then when you take it off again, you can restart the measurement and no data is lost. So if you also generally, if you halt the measurement, it saves every data after every measurement point. So things don't just get randomly lost. That's the important part. Yeah, it's keeping an eye out over the setup and making sure to stop it if people get close. Maybe make a warning to someone like, "Hey, watch out." So yeah, you don't want to have electrodes that aren't observed by someone because, and again, probably nothing will happen, but a person can get a shock, and an unlucky shock can kill. That's like every shock. If you're unlucky and it hits your heart at the exactly wrong time, and you have like a weak heart, it could kill. So for most people, it will just give you a shock. So,
Okay.
but like with any electrical shock, like if you're unlucky, it is way more dangerous than normal. So
maybe it also
I have
on the electrical current you choose, maybe also.
Yeah, exactly. So I have never electrocuted myself or anyone else. I've never even given anyone a shock using the instrument, using just those basic procedures. So I have a colleague, or former colleague, who once shocked a cow because a cow walked up to it while measuring and got his nose booped, and it just like stood up and walked away again because it's a cow. But yeah.
Okay.
But yes, but generally, yeah, it's keeping the safety switch on while you're moving things and making sure that no one is touching anything when you start measuring.
Okay. Thanks.
Yeah. Okay. And with respect to the learning materials, like so you mentioned like there's this manual which we
Yes.
and
and we also if you search LS2 on YouTube, Guideline Geo, we have some webinars and videos going through as well that are similar to this.
Okay.
Let me see if I can find it right now. And there's other, like the manual is very extensive. So it actually is able to answer a lot of questions. We do have other materials as well, like from there are webinars on it. So there's even some webinars when using Res to the nth. So I'll send you here's the YouTube link. And you can also, the student who'll work with it, you can have them look at it as well. So we have videos on doing surveys with different types, using some softwares, and so on. So
okay, I see. Yeah, so it shows even some examples. Yeah, okay.
Yeah, exactly.
Okay.
And there's some case studies on the Guideline Geo Resources website. So that's the link that I sent with the resource center. The resource center in general has lots of different materials to be used. So I just choose LS2.
Okay.
There's different materials and so on. There's some just the discussion about settings and so on. So there's lots of extra materials around it for those that want to look into it.
Yeah, there's application note, case study, instrument software for sure.
Yeah.
Okay. User manual, white paper. Okay.
Yeah, there's some case stories as well for the ERT ones, for example. So yeah, it's lots of things that we can find.
Yeah. Okay. That sounds good. Yeah. Okay. So that's I think that's and and this video would be available. You mentioned.
Yes. So I'll stop the recording and it'll take a couple of hours to upload. So I'll send it to you as a mail tomorrow, most likely. I'll send a mail to you with the link where you can access and download it, and it will be available for download for 3 months, I think. So yeah. It's just they usually take a couple of hours to upload. So I'll write to you tomorrow.
Okay, that sounds good. Thank you very much.
Thank you.
I'll stop the recording now. You should get a notification that it's stopped.